in the past or have done but we haven't turned in yet, or anything kind of in that neck of the woods? Victoria? 18? Sure. So 18, we're asked to do long division. It's worth pointing out that even if the direction wasn't to do long division, you'd notice that since the divisor there is not monic, it doesn't have a leading coefficient of 1, that synthetic division would be kind of inappropriate with the way things are set up. Now there's like some workarounds that we could do to make that doable using synthetic division, but we'd have to be a little bit careful about doing that, but the directions call for long division anyway, so whatevs. So I got my setup here. Notice that when I did the setup, I was missing a x squared term, so I included a 0x squared in the numerator, or in the dividend when I wrote it under the division bar. Everybody see that? Not critical that you have that here for the long division. As long as you're lining up the like terms vertically, everything will be okay. But I think it's like way less likely to make a silly mistake and do something goofy if you include the 0, which I always try to do. Okay, so we're going to start by asking ourselves, what times 2x gives me x cubed? Well, I know it's going to have to start with a 1/2, because I know 1/2 times 2 is going to give me the leading coefficient of 1. Very loud this morning in the hallways today, huh? And then I know that x squared times x is going to give me the x cubed, right? Everybody feel okay with that? A little weird that I'm having to use a fraction here, but like, not unreasonable. I'll go ahead and do. So I get x cubed minus 2x squared. And then we subtract down. But Mr. Kulik's recommended to you guys that instead of thinking about these as subtraction problems, to distribute the negative through and do it as an addition problem. So the x cubed becomes negative and the 2x squared becomes positive. So x cubed minus x cubed, or plus a negative x cubed, is 0. 0x squared plus 2x squared is 2x squared. And we'll go to the next spot. What times 2x gives me 2x squared? That just got to be x. And again, multiply that to both pieces. Oops, forgot to bring everything else down when I might as well say that. Still doing okay, Victoria? Yeah. Okay. And you'll holler at me if I do anything that you're like, what happened? But that goes for the rest of you too. All right, so I multiplied the x to both places. Wrote it below. We're going to subtract down. Before I subtract, I'm going to distribute that negative. So 2x squared minus 2x squared is 0. Negative 7x plus 4x is negative 3x. And then still bring down the leftovers. And one more question here. What times 2x gives me negative 3x? Well, this is a little bit harder to see. It's got to be negative, though, right? And then the coefficient has to be 3 over 2. 3 over 2 times 2 is 6 over 2, which reduces down to 3. Again, seeing a fraction there is a little weird, but like, all right, I can handle it, though. Negative 3 over 2 times negative 4 is going to be positive 12 over 2, which is just 6. And then we'll subtract down. Again, Mr. Kulik says distribute the negative to make it a subtraction problem, or turn into an addition problem. Negative 3x plus 3x is 0. 1 plus negative 6 is negative 5. So we'd say the answer there would be 1/2 x squared plus x minus 3 over 2 plus my remainder over my divisor. How's that look for you, Victoria? Again, kind of weird seeing that we had to use fractions in there, but once you've seen it, it's like, okay, if that's what we're doing, that's what we're doing. If you want to use those as decimals, if you want to use like 0.5 and 1.5, that's not inappropriate. Caution yourself if it was like 1/3 and 2/3 or something. It's using 0.3 and 0.6 or something is not going to work. You know what I mean? Since those aren't the same as the fraction. But yeah, that's okay. Who else with questions? Okie dokie. That's fair. We'll just kind of move on. So I think we had been looking at section 13.3 is where we had left off. Last time, I believe, we had been talking about using synthetic division and using the remainder theorem. We're going to kind of finish up on that topic here. So again, we're just kind of continuing on with this. So I'm just going to start with an example. So this example says to use synthetic division and the remainder theorem to evaluate f of -5, where f of x is 4x to the fourth minus 5x squared plus 7x minus 8. Okay, so I just want to talk through a little bit how we're using the what the directions mean in this case, because the directions are pretty specific on how they're asking us to do this problem, right? It's saying to use synthetic division, the remainder theorem to do this. If the directions were just to evaluate f of -5, what would we do? Just replace all the x's with -5 and type the thing into our calculator, right? Like bingo, bango, bongo, like no big deal. However, here the directions are very specific on how they want us to do this. So let's just kind of talk through kind of how we're using the remainder theorem and synthetic division to do this. So the remainder theorem tells us that if I take f of x and I divide it by x minus -5, that's going to give me some quotient plus some remainder over that x minus -5. What that's saying now, the remainder theorem says that f of -5 is going to be equal to that same r, that remainder we'd get from doing the division. And it's going to be this division that we're going to do the synthetic division on. Is that okay with kind of piecing together what the directions are really asking us to do? They're very specific there, so I wanted to make sure that we're clear. So basically, I just need to set up the synthetic division of f of x divided by x minus a -5. So here's my synthetic division setup. Who can tell me the number that needs to go on the outside of the synthetic division setup here? I need to put some number out here, right? What number has to go there in this case? It's -5, right? Whatever that number we're trying to evaluate is. Okay. And what are the numbers that need to go on the inside of the synthetic division bar to finish my setup? Who can tell me those numbers? Just shout them out. Okay, so 4, then what? 7, you said? 0, yeah. Why 0 here, Landon? Good. So you notice if you look at the polynomial f of x, we have a degree 4 term and we have a degree 2 term, but there's no degree 3 terms. We must include the 0 here when doing the synthetic division. You will not get the right answer if you do not do that. It's unrecoverable if you do not do that. You have to include the 0. Okay, continue, Landon. You mean -5? Excellent. Yes, of course. Okay. Everybody good with the setup for the synthetic division? Okay. And I will start. So we start just by bringing the first number down. And then I multiply the -5 to the -4. I write that answer in the next spot. And then add down. And then I just repeat. Does that all feel okay? So remember these numbers at the bottom of my synthetic division. So this is the remainder, the constant, the coefficient on x, the coefficient on x squared, the coefficient on x cubed. But for our problem, all we really need is the remainder. So the remainder theorem would say that f of -5 has to equal 2,332. As an aside, we could check this on our calculator. Right, if I go back to my polynomial and plug -5 in for the x's, I should get that same number. Let's do that real quick. Make sure when you're doing this, plugging things in, though, that you're putting a parenthesis around the negative number before you do the exponent. I see quite frequently students skipping that step and then getting the wrong result because the calculator is going to very strictly apply the order of operations, which means it's going to square the number or do the exponent of the number before it does the negative sign. So just to illustrate to you guys that if you didn't put the parentheses in around these -5s, you're going to get a completely different answer. And in fact, the wrong answer. Whoa, boy. Which frequently I'll see students come and show me this and be like, Mr. Kulik, I didn't get the answer that I was supposed to. And the reason is your calculator is going to do the 5 to the 4th and then make it negative. Because in the order of operations, the negative sign is coming at the multiplication step rather than the exponent step. So it's doing the exponent and then making it negative, which is why you have to put the parenthesis around the thing that's negative before you put the exponent on there. Just as a reminder, I think that I've seen that come up a couple of times on quizzes or tests recently, so I wanted to make sure I go back and point that out for you guys. Particularly if you're taking like an ACT or something soon, that feels like a classic ACT answer or multiple choice answer is going to give you the one that like you type this in your calculator like a bonehead. Oh, there's my answer, must be right. Oh, no. the ACT answer people make sure to put those kind of things on the possibilities. You know what I mean? Because they're sneaky jerks. I mean, not really. It's doing their job is to be sneaky, which means they're not really jerks. They're just doing their job. Okay. So we'll continue on now. So we've been, at this point, we built out this synthetic division thing, right? And we found that this is really nice because it can do the same thing as long division, but it's faster, which is super useful. And the tool, or the way we're going to be using this synthetic division going forward, is still going to be like looking for these x-intercepts or looking for these zeros for these functions, is the main way we're going to be using this. So we still need some more tools to kind of be able to do this effectively. So we're going to look at 2 more theorems today before we enter into the big process next time, Zach. Sure. So the rational zeros theorem says that for a polynomial f of x, which equals, so this is, again, this is our standard form for any polynomial, right? Don't be confused, right? The a's are just the coefficients, and we're using like a letter with a subscript to name our coefficients as opposed to like A, B, C, D, E, F, G. Mostly because a polynomial could certainly be more than 26 terms long, which means you potentially run out of letters. If we use a letter with a subscript, we have infinitely many symbols that we can use there, which is all we're doing there. Okay, so the theorem here says for a polynomial f of x, the possible rational zeros for f of x are of the form plus or minus p over q, where p is a factor of a naught, that would be the constant term, and q is a factor of a n, which is the leading coefficient. Before we roll and look at some examples of this, can one of you guys grab the door for me? Thanks. When we say rational in a mathematics sense, what do we mean? Does that mean the same thing as in English language use of the word rational? Like, oh, that's a logical zero that we've done. No. In mathematics class, when we say rational, what do we really mean? Anybody? Not real numbers, but it's related to a kind of number, for sure. The real numbers include things that are not rational numbers, but that is what we're talking about, is a type of number. Does anybody remember what the rational numbers are? Well, they include the whole numbers, but there are some things that are not also whole numbers. Look at the root word of rational. The root word there is ratio. What is a ratio another word for? A fraction, right? We're just talking about fractions, things that can be written as fractions. So a whole number can be written as a fraction, right? Like the number 4 I could write as 4 over 1. Now, are there numbers that can't be written as fractions? Yeah. For example, there's one used in geometry a whole heck of a lot. Pi would be an answer. There is an example of a number that can't be written as a fraction. Other examples might be e. You remember that from last year, maybe. Fingers crossed. Or even things like square root of 2 or square root of 3 or square root of 5 or square root of 7 are all examples of things that can't be written as a fraction. Okay? So, is the rational zeros theorem inclusive of all possible zeros? No. And in fact, when we solve polynomials, we saw that lots of times we get answers with square roots in them. But if the answer doesn't have a square root in it, well, this will probably find it. Okay. The other word I want to mention is the word factor. So what does it mean if something is a factor of a number? Great, you can multiply something else by it to make that number. So for example, we might say that 2 is a factor of 6 because 2 times 3 gives us 6. Great. All right, so let's do an example here. Those were the technical terms here. I think I'm going to start abbreviating the phrase possible rational zeros just PRZ, kind of from here on out, because it's going to come up a lot, and there's a lot of letters that I can skip. Mm-hmm. Okay, so let's say we want to find the list of possible rational zeros for the polynomial 3x to the fourth plus 4x squared plus 7x plus 4. So my P is the constant term. So the factors of 4 are 1, 2, and 4. Everybody agree? My Q is the leading coefficient. The factors of 3 are 1 and 3. So my possible rational zeros are going to be plus or minus the factors of P over the factors of Q. So I'm going to take every factor of P and write it over every factor of Q. Now notice here, each of those could reduce if you wanted to write that as 1, 2, and 4. That's okay. Feel free to do that. I'm writing it with the denominator 1 right now because it's demonstrating kind of what's going on. Now, do I know any of these are actually zeros for this function? Do any of these have to work as zeros? No, man. None of them have to. But, can somebody grab the door for me? Thank you. Let's put the doorstop back in. It seems like the noisy people have left. Do you mind, Maria? Thank you. I appreciate that. If you just put it in enough so the door doesn't latch, that's okay too. I don't think you got it. I know. Just stick it in the crack there. Yeah, just as long as it keeps, as long as you don't have to get up. That's all I care about, you know. You've done enough favors. All right. So yeah, remember that the number of zeros is at most 4, right? Could be 4 zeros, could be 3, could be 2, could be 1, could be 0 x-intercepts. So this might have 0 x-intercepts, so none of those would be a possibility. But it could also have 4 x-intercepts, and they could all be non-rational, right? The term we use for that is irrational. Like the zeros could be like negative square root of 2, positive square root of 2, negative square root of 3, and positive square root of 3. None of those are on my list here. Is everybody cool with that? That even though we've made this list, we don't really know anything for sure. Now, is there a way that we could help narrow this down as to knowing which ones are even good ones to check? Now, back in my day, no, man, it was pretty brutal. You just had to like kind of guess and check. But you guys have a better tool accessible to you than when I was a high school student, where yes, these things existed, but they were not standard at all. What do you suppose that tool is? Well, we had calculators, you jerk. It's not like I was working with abacus. I'm not that old. No, we had calculators, but we didn't have graphing calculators commonly available. Yes, they existed. You had like TI-81s and 82s floating around out there. But most people, I don't know that I saw one until I was like in college. So like, yes, I know they existed, but like nobody had these things. So what you could do, I just got to change the mode. We're in different class last time. Is you could type this guy into our calculator and take a look at the graph and try to make some intelligent decisions about what looks like possible x-intercepts. And because I was using this for a different class, before I graph this, I'm just going to do zoom standard so it resets the window to something sensible. So let's see. Look here. This looks like about a little bit less than -1. So I think -4/3 would be a reasonable guess. Maybe that one will work. And then I see another one over here that looks like somewhere in between 0 and 1. So I guess that could be +1/3 or +2/3. I'm not really sure if any of those are actually right, but those are close enough to the picture that you might want to check them. Does that make sense? All right. Let's look at another theorem that, again, was really useful to me as a high school student, or is a little bit less useful to you, given that your technology advantages are considerable compared to Mr. Kulik's. You guys had like running water, you have electricity, you're not working by candle on a chalk slate. These are jokes, like this is what 18th century America would look like. It's clearly, I'm not 150 years old, but ha ha ha, Mr. Kulik, so funny. All right. So we would say for a polynomial f of x, with positive leading coefficient, when we divide by maybe we'll say use synthetic division to divide by x minus k. We get two possibilities. If that k is non-negative and every number in the bottom line of your synthetic division is non-negative, then k is an upper bound for all your real zeros. No, maybe we'll be of f of x, I guess we'll be specific. And if k is non-positive and every number in the bottom line of your synthetic division is alternately non-negative. I guess here I'm going to write it out, and then non-positive. Then k is a lower bound for all the real zeros of f of x. So a couple of just pieces of vocabulary. When I say upper bound, what does that mean? If k is the upper bound for the real zeros of f of x, that means none of your zeros could be bigger than k. Right? And if it's a lower bound, we mean that none of the zeros could be smaller than k. Right? So basically what this does is it says, okay, if I can find an upper bound and a lower bound, I know everything has to be in between that. Because what is the real upper bound and lower bound we start with before we've done anything? Negative infinity to positive infinity, which is a pretty frustrating bound because it's essentially unbounded. Ew. The other thing worth mentioning here, when we say real zeros, does that mean like, oh, that's one that you actually find and it's not like something you made up, right? Like a made up zero would be like, you know, squiggly taco. So real zeros just must be like a number, right? No, man. We're talking about like the real number set, which is essentially anything you can write as a decimal. So that's all of them that aren't imaginary. We don't mean like, oh, you're not talking about like those made up numbers that I had when I wrote my fantasy science fiction novel this summer, huh? No, man, like cat scratch is not a number. I got 8 cat scratches. What are you talking about? Anyways, let's just do an example here of this and then we'll be done. All right. So let's say we have this guy, and we want to show that every real zero for this polynomial is on the interval from -5 to 4. Really what we're really saying here is just to show -5 is our lower bound and that +4 is the upper bound. Everybody's cool with that? So really just doing the synthetic division. That's all it says to do that, or what all our theorem says. All we need to do is to look at the bottom line of our synthetic division. So let's just rock and roll that. So I'll just do my two synthetic divisions with my lower bound and upper bound. Oh my goodness, that's 212, 848, that's 833. All right, so what can I conclude here? We're working with the -1, so we're in this piece. So I need to check to make sure they're alternately non-negative and non-positive, right? So positive, negative, positive, negative. So I can conclude that -5 is a lower bound. On this one, we have our k is positive. So we need that all of them are positive in my lower line. Positive, positive, positive. So I can conclude that 4 is an upper bound. Landon.
So say you're doing a -5, right?
Mm-hmm.
And you do the positive, and that -5 is just a 5, and you made it negative. So is that not a lower bound?
So Landon's saying hypothetically, if I had a 5 here instead of a -5, then this does not meet the criteria. However, if this instead of being a -5 was a 0, that's okay. Because again, it's alternately non-negative, which includes zeros, and then non-positive, which is including 0. Go ahead. Mm-hmm. So I have positive, non-negative, positive, you know what I mean? I should say non-positive here, but you get the idea. All right. So let's kind of put these new ideas together, and we'll do one final example and call our quits for today, okay? All right, so we want to find all the real zeros. So how many possible zeros could I have? In this problem? At most 3. So 0, 1, 2, or 3 possible zeros. my possible rational zeros are going to be the factors of 30. Oh boy, Mr. Kulik, you picked a booger of a problem here. How many factors of 30 do I have? Too many over my factors of 6. Oh, Mr. Kulik, this is so painful. There's so many possibilities. I knew. You know what? We're going to just do this. Move that down here. Move this up here. Because this is going to get a little bit lengthy. Again, this is my P and this is my Q. All right, so I have my every P over every Q. I'm not going to write these as fractions that don't need to be written as fractions in the interest of Mr. Kulik's sanity, because it's already going to be, oh, so long. So those are all my P's over 1. And then all of my P's over 2. I'm not going to write the duplicates. So like 2 over 2 is 1, so I'm not going to write that. Is everybody okay with that? Again, just in the interest of time. So over 3. Again, I'm skipping 3 over 3. I'm skipping 6 over 3. I'm skipping 15 over 3 and skipping 30 over 3. And then, so I'm skipping 2 over 6. I already have that. Skipping 3 over 6. I have to have 5 over 6. Skipping 6 over 6. Skipping 10 over 6. Skipping 15 over 6, skipping 30 over 6. Those are already done. Okay. Now that I've got my list here, I'm going to go look at my graph. So I'm just going to go ahead and type this bad mama jamma into my calculator here. And then hit graph and take a look. Again, I'm looking for x-intercepts. So let's see, this is -1, 2, 3, 4, 5. Looks like -6 is 1. And then I got 1 over here. It looks like maybe -1/2 or -1/3 or -2/3. We're going to do it this way. We're not sure. Based on my picture, I can't tell the difference between those ones, right? But I know it's between 0 and -1. And then we got here, this is between 2 and 3. So I think the only thing that comes between 2 and 3 is 5 over 2. Everybody so far so good? All right. Now I'm going to start doing my synthetic division with one of these. Which one do you think is the most obvious choice to start with? -6. Why? Well, there's really only one option what I think that could be, and that one option is not a fraction. So, like, you know, it's the old KISS strategy. You know what KISS stands for? Keep it simple, stupid. Right? So, let's go. I got remainder 0, which means that's good. That's a factor. So what I can conclude from this is that 6x cubed plus 23x squared minus 83x minus 30 factors to x plus 6, since when I divided by negative 6, I got remainder 0, times 6x squared minus 13x minus 5. Everybody's okay with that? And this is actually far enough for me to be able to finish this guy out. So I know one of my zeros is here at negative 6. Another of my zeros can come from this piece, which if I set equal to 0, I can now solve. Why can I solve this piece directly when it's set equal to 0 like this? What's different about 6x squared minus 13x minus 5 as opposed to 6x cubed plus 23x squared minus 83x minus 30, where I couldn't have done the same thing there? Dude, it's quadratic, right? Can we solve quadratics? Heck yeah! What method would I use to solve this quadratic? There's two reasonable answers. I think one of them makes more sense than the other, though. You could try to factor this. It is factorable, but it's kind of a pain in the butt to factor. Why is this one kind of a pain in the butt to factor? The leading coefficient isn't 1. But what other method can we use on all quadratics all the time? The quadratic formula. Yeah, so x equals negative b plus or minus b squared minus 4ac all over 2 times a. So 13 plus or minus 169 plus 120, so that's 289 divided by 12. The square root of 289 looks like a perfect square to me. I'm pretty positive well, I know it has to be. I don't remember what it is. Is it 17? Yep. So that's 13 plus or minus 17 over 12. So if I add those, I get 30 over 12, which reduces down to 5 over 2. And if I subtracted those, I'd get 4 over 12, which reduces down to negative 1/3. I guess I should have said negative 4 over 12. But those are my 3 x-intercepts, or my 3 zeros. Is that okay? Now, Mr. Kulik, could you have done something different here? Yeah, man. Because we still had some more stuff on our list, right? What you could have also done is you could have kept going. If I use a second value from that list, which one would you pick? Man, pick the 5 over 2 because we're pretty positive that's the only option for that one. The other one, we don't know which one of those it is. I'm going to write it as 2.5 rather than 5 over 2. So we repeat here. Let's use a different color here. So bring the 6 down. 6 times 2.5 gives me 15. And then 2.5 times that is 0. Hey. So what is this saying then? It says that 6x squared minus 13x minus 5 is equal to x minus 2.5 times 6x plus 2. And if I take what I had before, along with this, if I put those two things together, we can say 6x cubed plus 23x squared minus 83x minus 30 was equal to x plus 6 times 6x squared minus 13x minus 5. That's from the first step. And then we can say from the second step that 6x squared minus 13x minus 5 is x minus 2.5 times 6x plus 2. And then if we set each of these pieces equal to 0 and solve, we're going to get those same 3 zeros. So negative 6, 2.5, and negative 1/3. Does it matter which way you do this? Nada, man. One way you had to do the quadratic formula, the other way you had to do an extrasynthetic division. I think that's about the same amount of work either way. It's up to you. Whatever you like to do is I'm cool with. What do you guys think? This is a good place to stop. You'll notice on the board that we've added some more problems to the problem set for Sunday. So we've added on 32 to 35 in worksheet 1. So a little bit more that we've tacked on there. So the current problem set for Sunday is 13 to 14, 20 to 23, 32 to 35. Did I say 20 to 23? I meant 20 to 31 is what it says up there. And then worksheet 1. All of that's reflected on My Notre Dame. Any questions for me about any of this stuffs? Okay, well, let's stop.